Rolling motion is ubiquitous in our lives. You ride a bicycle, you have a wheel that is rolling along the ground. Okay? Car tires are rolling. There's all sorts of things that roll in factories and so many machines. Okay? So understanding how rolling motion works is really important. So to think about it, rolling motion, especially rolling without slipping, means this wheel, as it goes along the ground, is rotating, okay, with some angular speed, and it's moving with some linear velocity. We call it a translational velocity. Okay, so the thing is moving along, that's its v, and it's also rotating. And for the case of it's not slipping, that means the point right here has no velocity relative to the ground. It's not skidding at all. So the point of the wheel touching the surface is not moving. So that'd be rolling without slipping. So with just that basic features, we can actually analyze this and see that there is a very specific relationship between this omega and that speed there. Okay, now to do so, I want to look at a different picture. And I'm going to look at a long, skinny rod that is pivoted about one end, okay? And it's rotating, so it's got an omega. And if I look at different points, let's say right here and at the end right there, and I want to find out, well, what's its speed? Well, we know that the velocity at some point r, measured from the pivot point, is going to be equal to that distance from the pivot point times omega. Okay, that's a relationship we saw way back when we studied the beginnings of circular motion. Okay, so that means that this point is moving with some v that's equal to, we'll call this r over 2, sorry, actually L over 2, with this rod being length L. So that's the distance from the pivot to where I'm measuring that velocity times this omega. And remember, omega is the same for this whole thing. It goes through the same angular distance. It goes through the same angular distance no matter where you're at. Now this one, the velocity would be, v here would be the full L times omega. Okay? So that's something that we understand. That's a review. Now how do we apply that to this? Okay, so if we think about looking at a line and put some marks on this tire. We'll put a mark here, and we'll put a mark here, and we could put a mark here. And we look at them and see what they're doing for a very small angle. I mean, teeniest of angles, just the teeniest of rotations. This point right here effectively doesn't move anywhere. It's really not going anywhere. Even though at a much later time, this point will be up as the wheel has rotated. Okay, but for a very small amount of time, this really hasn't gone anywhere, so it acts like this pivot. Okay, and then that means this one has moved, okay, with some speed, and we can call that Vcm. It's the center of mass speed. That's where the center of the wheel is, and it should be equal to half this total length, this diameter. Okay, so this Vcm is going to be the diameter over 2 times that angular speed. Okay, how much is that spinning? All right, and then this top one ought to be twice that fast. Okay, V here is going to be d times omega. Okay, so we can see that. Now the thing I want to find out is how is the angular speed related to the center of mass speed? The center of mass speed is the thing we can see. We see the car moving along in the center of the wheel. If the car is moving 30 meters per second, the center of the wheel is moving 30 meters per second along the road. Okay, otherwise the tire would rip off of the car. Okay, so the center of mass is something we can measure really easy. And we want to see, well, how is that related to the rate at which the wheel is just rotating about that center? Okay, so to figure that out, we can do something that is pretty cool. This picture here of rolling motion can be built up from two separate pictures. One is as if we're just watching that wheel not rotate but just move along. Okay, so we're watching this whole wheel as if it's moving along. And if that's the case, all pieces of it move at the same speed. Okay? So they're all moving at the same speed. So I'm focusing on just these three, but I could focus on any dot anywhere. And then we can consider, well, what is the wheel doing if it's just spinning about its center of mass? So it's not going anywhere, so the speed here is 0, but it's just spinning about its center. Well, that means the top speed will be this way, and the bottom speed will be that way. So if we look at, again, these three dots here, the one at the bottom, one at the top, one in the middle. Well, if this is the real picture, can I build it from these two separate pictures? Can I add this one plus this one to equal what I know about real rolling motion? Like that. Okay. And if you look, that could work out abstractly. This is just an idea. This could work out abstractly if this velocity is equal to that velocity in magnitude, so that we get 0. Okay? If it is, that means this velocity is equal to this velocity, and this velocity is equal to this plus this, but this equals this, so it's twice the top, which is what we got before. Okay? Now that was kind of an abstract presentation, and there's a much more rigorous mathematical way of showing that. But what I want to point out is this is a really powerful and accurate way of analyzing rolling motion, is to break it into its two types of motion. You can break it into translational motion and rotational motion. And by doing that, by noting that this speed here is equal to this speed here, which is the center of mass speed, then this speed, which is v tangential, which we just said is equal to v center of mass, okay? But v tangential itself is equal to r omega, where r is the distance from the pivot point, which is, in this case, is the center, times omega, okay? And what we said up here was that the center of mass is equal to d over 2, which that's just the radius of the wheel. So we have matched it with these two models. Okay, so this picture here is an accurate way of describing how this really works. Now I want to point out something that's really cool, is by recognizing rolling motion is just the abstract, the kind of physical sum of translational motion plus rotational motion, then we could do all sorts of things with it. So for example, we could say that K, the kinetic energy of rolling motion, okay, I'll put rolling, is just equal to the kinetic energy of translation or moving. So that's up K trans. So the translation means to move from one point to another, plus K rotational. This is K rolling, this is K rotational, and this is K translational. All right. Now, if that's true, let's try and figure out how this works. Okay. This is basically a pivot point that this disk is moving around that point. Okay. So I want to go back to this example to use this example to show what we're the power of this process. Okay. So let's focus on this one. This whole thing that is pivoting about its end is as if the center is moving. Okay. And then it's rotating about its center. So to look at that, here's this rod again. Center's there, and that center of mass, let's say it's just spinning about a point. So I have this fixed in space, and this is spinning about the end of it. Okay. Now I'm going to put down here, if that's the case, if I have a rod spinning about its end, I know the moment of inertia of that is 1/3 ml squared. Okay, that's from the table in the text. Okay, now I'm going to see if I can get that by looking at this in terms of two parts of its motion. I'm going to look at it in terms of the center of mass is just moving around. Okay, so that'd be the center as a point is just moving. And then this thing is rotating about its center. So you can imagine that every time it goes around one circle, this end was up, it's down, and it's up again. So this is rotating around its center of mass once per rotation of the center of mass. Okay? And so looking at that, if I think about all the masses concentrated here, then I get this is going to be 1/2, okay? And then the rotation of the a point particle flying around in a circle is going to be just mr, which is L/2 squared. That's a point particle. That's moment of inertia for a point particle. And then I have omega squared. And then I add to it the rotational about the center of mass. Okay, and that's going to be a 1/2. And then about its center of mass, we know that the moment of inertia for a rod about its center, looking at the table in the text, is 1/12 ml squared. Okay. And again, in this case, I'm just breaking it up into two types of motion. What is the center of mass doing? And then what is it doing about the center of mass? So this is like the center of mass is just moving, and this is rotating about the center of mass. In this case, the center of mass is moving in a circle, but the whole thing is spinning about that center of mass at the same rate at which the center spins. So center of mass motion, and then rotation about the center of mass. Okay, so I've got this, right? And then if you collect all your terms here, you can see that we have some L's squared, we have omega squared, some M's. If we pull that out and make it look like a 1/2 times something omega squared, then this should be I for a rod rotating about its end. Okay, this is collecting the center of mass moving and then the rod spinning about its center. And if you collect the pull the halves out and omegas out, we collect everything that's inside these brackets. We have a 1/12 ml squared. This 1/2 squared ends up being 1/4. So we have a 1/12 plus a 1/4. And 1/4 is the same thing as 3/12. So 3/12 plus 1/12 is 4/12, which is 1/3. And we indeed get what's in the text. Now, the way this number was gotten from the text was just integrating it directly, the way we found all the other tables. But this is a much easier way to find that, finding more complicated geometries from that basic set of geometries that are given in the text. Okay, so this was quite a lot. This video is quite a lot, but what I want to review is saying rolling motion has a couple things very important. One is that the center of mass velocity is equal to the angular velocity times the radius of the wheel. Okay, that's one important thing. But even more important, that's applicable for rolling motion and applicable for any type of complex rotation, is that you could take the full motion and break it into motion of the center of mass plus motion about the center of mass. So in the case of rolling motion, you can get it from the thing just moving, so translational, plus the rotation about a stationary center. Or we can apply it to something more complex like this, where we can still look at the center of mass and it's moving in a circle, and then this rod is spinning about that center of mass. We were able to break it up into two pieces. Okay. So that's the main idea, but this idea of breaking complex motion in these two pieces is really, really a broader and more important topic.